All right, so AP Physics, let's get rolling again here. We've got a couple things to take a look at. If you remember last time, we had our current model. You'll have to excuse them in my teaching bunker here, by the furnace. So we had this current model, and we were talking about circuits, electricity, and we were first just looking at how the current flows around a circuit. And we saw the more flow, more glow in terms of light bulbs and ranking light bulbs. We'll take a quick review of that in a second. We saw the second rule, and I've narrowed these down to like 3 different rules. I know we had 4 or 5 of them on the board, but these are the 3 main ones. So current is related to resistance through this formula, Ohm's law, which we'll take a look at more in-depthly when we solve circuits. And then we have number 3, which is conservation of current. Which means that I don't lose current when I go through a bulb or any resistor. It just keeps flowing. What goes in comes out. Okay. So an example of what we were doing when we left off would be here. We've got 4 bulbs and a switch. And if I look at, say, this current comes out of the battery here. We're not talking any numbers yet. We'll get to those later. But that current comes out and it lights up this bulb, right? Then it comes through the bulb, conserved, so the same what went in comes out. At this point the switch is open, so all the current goes this way. So if I were to rank these 3 bulbs, okay, these 3 bulbs in terms of current or brightness off the bat with the switch open, I'd say A equals B equals C. Right? Because they're all basically in what we'll call a series circuit. Okay? But now if I were to go in and turn the switch on, I'm going to get a change, right? So now if I close this switch, that means that the current's going to have to choose now one path or the other. Now one of the ways that we talked about reducing resistance is adding this branch. So I've added a pathway. So the battery is pretty happy about added pathways. That means it's going to send out more current. So if we want to look at the change that closing the switch did to bulb A, we'd say that, ooh, it got brighter. Ooh, it really liked that because A is an indicator, which means it gets all of the current from the circuit. Okay. So now this huge amount of current, or increased amount of current, goes here, but now it has to split. So that means instead of B getting all of it, B's going to get some of it. And in fact, the pathway through B is a 2 bulb pathway, which means more resistance than bulb D. So that means that B is actually going to not even get half of the current. It's going to get a little less than half. Okay, D lights up, and it's going to be brighter now than B. So if I were to rank these, I'd say A is the brightest, followed by D, followed by B, which is equal to C. Okay, and the reason for that is when it gets to this point, it has to split, so D is going to get less than A for sure, but it's also going to get more than B because its pathway is only a single bulb pathway versus a double bulb pathway. Okay. Now if I were to compare we said what happens to A when I turn the switch on, A got brighter, but I can't necessarily answer what happens to B or C when I turn the switch on. It's one of those situations where now there's more current, but B only gets a share of it. Okay? It has to share some of that the other direction. So it's a problem of, is less of more a larger amount than all of less? Right? We went through that discussion on the last day before all this took place. So we call it a pizza problem, and we don't know if sum of more is equivalent or more or less than all of less. Okay? So that is where we left off. What we're going to get to now moving forward is, and I got a couple problems for you that I'll link in Schoology later today. Let's switch over to now some numbers. Okay, so let's take a look at some numbers here. I've got a circuit now with some values written on it. And if we go back to our little current model, we talked about this guy here, which is voltage equals IR. Okay, that's Ohm's law. So Ohm's law, I'll kind of leave that up here in the corner. this is useful because A, it's pretty simple. The voltage is equivalent to the current times the resistance, but it's also useful because it can be used on individual parts of a circuit, or it can be used on the circuit as a whole. Okay, and that's kind of important, and you can do the two interchangeably. You can use this over and over and over and over again as you work through a circuit. So let's take a look at solving now, what we call solving an electrical circuit. So V equals IR. So let's say the first thing we need to do in solving a circuit is I need to figure out the total resistance in a circuit. Now, to do the total resistance in a circuit, I'm going to have to sum up all of the resistors in that circuit in some way. Okay? So let's look at a couple different ways that we sum up the amount of resistance. Okay? So if I have resistors in series, and you'll find this on your formula sheet, resistors in series, I simply can add them up. Okay, so R1 plus R2 plus blah, 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 however many I have. And that's the equivalent resistance. If I have resistors in parallel, the total resistance for all resistors in parallel branches is kind of a funky way, a little bit like our lens equation. 1 over R1 plus 1 over R2. Okay? And actually it doesn't just sum those up and equal. It's like just like the lens and the focal point equation where we figured out image distance. It is 1 over the total resistance in parallel. Okay? Dot, 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 dot. So again, a quick example of something like that. If I had two 10 ohm resistors in parallel, I would say 1 over 10 plus 1 over 10 equals 2 over 10, or 1 over 5. And that means that my total resistance of this section is 5 ohms. And I can treat this like it's just one resistor with 5 ohms. Okay? So that's a quick description of how you go about summing up these circuits. So let's go back to our main circuit now. And we'll take a look at, first things first, you start to break it down from the smallest point out to the whole circuit. So I look at one little section right here, and we'll say, what is the equivalent resistance of these two? If I had to take these two resistors out and replace them with one resistor, what would I get? And these are in series, so I can just add them up. So I'm going to say 5 plus 5 equals 10 ohms. So I can now kind of rewrite this whole section and say this is like one resistor that is a 10 ohm resistor, and I can kind of ignore that section right there and say, oh, it's just one 10 ohm. Now I've got these two to deal with. I've got two 10 ohms that are in parallel. So I got to go to that parallel connection, which is 1 over 10 plus 1 over 10 equals 2 over 10, or 1 over 5. Okay, and we did this in the last example just now. So that means that this whole section here acts like one 5 ohm resistor. So let me inside here draw a little miniature circuit. I've got a 7, and now I've basically just got a 5er. Okay, because I combined these two to make 10, and I combined the two 10s to come up with one big 5. So I've got a 7 and a 5 with a 12 volt battery. So now I can solve this little easy section, 7 plus 5, because they're in series, and I end up with 12. So another little miniature circuit. This behaves exactly like this circuit. Okay, a 12 volt battery and one 12 ohm resistor. So that little circuit here acts exactly the same in terms of current as the giant one out here that has all the sort of complex branches. Okay. So now once I know that this is a circuit with 12 ohms, I can apply my Ohm's law, and I can solve it for how much current is going to be sent out by the battery. Okay, so let me clean this up a little bit. Kind of keep in mind to remember what ohmage we had for our little sections, just in case we need them later. Okay, so now if I go a 12 volt battery, and I said the equivalent resistance on here was 12 ohms, it's an upside down horseshoe, equals 1 amp. So that means that 1 amp, and remember we always come out of what we call the positive, and go in, return on the negative. So 1 amp comes out of the battery. 1 amp goes through the 7 ohm resistor. Okay. 1 amp comes this way. Now 1 amp has a choice. It has to decide how much to go this way and how much to go that way. This pathway has 2 resistors in it. So if we look back at when we talked about the bulbs, we said, oh, those 2 bulbs, that's a bigger resistance than the 1 bulb in our previous example. But that was assuming all these bulbs are identical. If you look at what situation we have over here, these are not all identical. These are 5 ohm resistors, and this is a 10 ohm resistor. So the way that I check deciding how much it's going to split is I sum these 2 up and say, well, this is like a 10, and that's a 10. So that means that it's going to split evenly, which means 0.5 ohms, or amps, is going to go this way, and 0.5 amps is going to go that way. So that means 0.5 amps goes through this ohm resistor, 0.5 amps goes through this resistor, comes out of that resistor, 0.5 amps goes into this resistor and comes out of that resistor, comes back together. The 0.5 from this side and the 0.5 from that side comes back together to make 1 amp return all the way back to the battery. Everything has to work out. Okay? So far we've solved this circuit in terms of the total volts, the total amps, and the individual amps and resistance of each piece. Okay? Now we have one more part of this puzzle, which is we have to figure out how many volts each of the resistors uses up. Okay? I have a total of 12 to use. This is the pump. Okay? The 12 is the pump, and that 12 is going to be able to push the current through. But unlike current, voltage actually does get used up as you move through elements. Okay? So if I have 12 volts, that means by the time I get around any single path, I'm going to have used up all 12 of those volts, so I can go back to this side with none. Okay? And that's a way that we're going to see how you can check these out. I can check if I've solved my circuit correctly by following a single pathway with my pencil, and if it adds up to the total voltage that the battery has, then I've done it right. And every pathway that I choose should always add up to the same total voltage of the battery. Okay, so we'll check on that. So I'm going to now take a look at this in terms of volts. Now, way back at the beginning of this video, I said we can use this equation, Ohm's law, both on individual parts and on the whole. So far we've used it on the whole right here, 12 volts, 12 ohms, 1 amp. Let's use it on individual parts. Okay, 7 ohms, 1 amp for this resistor. Okay, 7 ohms, 1 amp. So 7 times 1 means that 7 volts, and also let me switch colors here. 7 volts is then going to be consumed by this resistor. Okay, 7 volts. So if I'm a 12 volt battery, I've already used 7 of it right here. That means I've got 5 left. Okay, if I go to this one, I can say 5 times a half means 2.5 volts. Okay, half of 5. 5 times a half, 2.5 volts. 10, what's half of 10? 5 volts. Okay, so now let's do that check to see if we've done this right. If I start over here with 12 volts and I follow this pathway, I've used 7. I come this way. If I have to pick a direction, okay, if I go this way, I use 5 more. So that 7 plus that 5 means I come back having used all 12 volts. I should be able to get that with any choice I make along the circuit. So if I come up as 12 volts, go through that way as 7, but now choose to go this way, I go 7 plus 2.5 plus 2.5 gets me to 12 again. So now I know that I've done this correctly. So the full solution to the circuit means I've detailed the volts, amps, and ohms of every single element in this circuit. Okay? So this was a pretty easy one. Let's walk through one more, a little bit more challenging one. Okay? So here I've got one that's got a few more elements in it, and we're going to do the same thing. The first thing we're going to do is summarize the total resistance of this circuit. Okay, so we're going to sum up all the elements, and again we start out in a small section, the smallest spot, and we work our way out to the bigger section. So if I look at the smallest individual component here, it's going to be the 4 plus the 4. Okay, so they're in series, so I'm going to add them up. So 4 plus 4 equals 8. So now I have an 8 ohm. Again, this just acts as though it's one 8 ohm resistor. I've got an 8 ohm and I've got an 8 ohm down here. So now I'm going to have to do the 1 over 8 plus 1 over 8 equals 2 over 8, which equals 1 over 4. So this whole section here, and I'll just write it really big, acts like one 4 ohm resistor. This whole section of 3 resistors, okay? Because we have to use the denominator there. So I've got, now this section, I've got 1 over 6 plus 1 over 12. Okay, to get common denominators, I'm going to have 2 over 12 plus 1 over 12, which is 3 over 12. And that 3 over 12 gets reduced to 1 over 4. So that means that this whole section acts like one big 4 ohm resistor. Okay, so I've got a one big 4 ohm resistor up here. I've got a 4 there. I've got a 4 there. That equals total 4 plus 4 plus 4 is 12. So if I apply my Ohm's law, voltage divided by resistance equals current. So I'm going to have 12 volts divided by 12 ohms, and I'm going to be left with that 1 amp again. You can see I've tried to make these mathematically pretty straightforward. Okay, so that means 1 amp leaves the battery. Okay, let me clean this up a little bit so we don't have too much going on. Okay, that 1 amp leaves the battery. It comes to this place. Now here I've got a choice, and I've got one pathway that's 6 ohms, one that's 12, so they're not equal. So I don't split this 1 amp equally. I split it to the right. Current is going to favor the path of least resistance. So how do I do that? Well, it's proportionally. So that means that the 1 amp has to get split so that half as much comes this way as went that way, right? Because this is twice the resistance. So how do I split 1 into basically thirds and have 2 of it go one way and 1 of it go the other way, right? Well, that means that I'm going to have 0.33 amps come this way and 0.66 amps go that way. More current goes to the path of lower resistance. They come back together as 1 amp after they leave. They come out this side, and I've got now 1 amp going through that single resistor. 1 amp comes here. Now these two paths are 4 plus 4 is 8, so this pathway is 8, and this pathway is 8. So now they can split evenly. So I got 0.5 amps going this way and 0.5 amps going this way. I've got 0.5 amps going through this resistor, and I come back out as that 1 amp again. Remember, conservation of current. I go back into the battery as the 1 amp. So now I've got amps on everything. I need to get my voltages of everything. So again, I can apply this Ohm's law to my individual sections now, and I can say that I can start here and say, well, I've got 1 amp and 4 ohms. That means that's 4 volts. Okay, and again, if I do this right, I'm going to be getting to the point where I can take any single pathway and I can work my way around and end up with the 12 volts. Okay, so if I say 6 amps times 0.66, 6 ohms times 0.66 amps, I basically get 4 volts this way, 3.96, and then I've got 12 times 0.33, which is basically 4 volts as well. One of the patterns we'll see is that when I get a parallel branches will always get all and equal of the voltages. Okay, so you'll always see these the same. So let's apply that to the next one. I come to this section. I've already used up 4 and 4, so I know I've got 4 left. So I know 4 volts must go this way. And I know 4 volts must go this way. You can see 8 times 0.5 is 4 volts. 4 times 0.5 is 2 volts, and 2 volts, so that's where this 4 volts comes from. Okay, and if I now choose any single pathway, let's head out and go this way and pick this direction. I've used up 4 volts. I come back together. I'm up to 8 volts. I can go this way. I've got 10, I've got 12, and I've used up all 12 volts. So that knows that that pathway was correct. Let's try another pathway. I can go out as 12 volts. I can come down this way, and that's 4. I can go back up and around. I'm up to 8 now. If I go this way, I'm at 12, and I've done it correctly because they all add up to 12 volts. Okay? So you're going to get a picture of a circuit like this in Schoology, or several of them, and I want you to go through and sum up the resistance, right? Find the total current that comes out of the battery, then go through each element and find out the amps that go through each resistor and the voltage of each resistor. Okay, what we will call solving the circuit. Okay, that's going to be your assignment. You're going to have a few of these to do this week. You can always ask questions through Schoology or email, and we'll go from there. Okay, I'll also post another challenge question out there in terms of circuit diagrams and wiring for you to work on, and in all these cases with these things, these pictures, I'll have assignments in Schoology that you can post a picture of your completed circuit. Okay, and again, when you draw it, make sure you're drawing it fairly neatly so that I can tell. Ideally, you're using multiple colors, and you're taking a good clear picture of the whole thing so I can check it that way. Okay, thanks.